So in the next part, we are going to consider the propagation of TM waves inside the rectangular waveguide. Only TM, how it propagates. The general equations we are already familiar with. Now we will consider only TM waves. Okay. Equivalent to that, we have the TE waves coming in the next half. Okay. So one of them will go slowly. We'll understand every concept and we'll go. As the second part will be easier for us, we'll go faster. Okay. Right. Okay. So the next topic will be the propagation of TM waves in rectangular waveguides. Okay, so let's start with the equation, one form of equation which we already know. Okay, so that is called as the wave equation, right? So the wave equation of the TM wave. So wave equation is referred as the second order differential equation which we have, partial derivative, right? So that is dou square Ez divided by dou x square plus dou square Ez divided by dou y square plus h square times Ez, right? Recall this is what we had written in the previous class. Right. Now, so this is a equation. So let me call this by a number. It's equation number one. So basically, this partial differential equation can be solved to get the various field components as such as Ex, Ey, Hx, Hz. All right. So we had looked at one format in which you can try to get the solution in the previous session, but now we'll apply the appropriate variable separation method to get the equation. Now we'll try to bring the sign. So the trigonometric functions will come into picture in the solution. Okay, so previous solution were not containing the trigonometric relationship. Okay, so now in this solution we are going to have like this. Okay, so to find the solution, right, we need to assume. So okay, I'm going to the basics of mathematics. Maybe in uh, one of the engineering mathematics subject, maybe I think second or the third version of engineering mathematics, we have studied the solution of differential equation. In that we also have studied what is called as a specific method separation of variables. All right, so let me try to bring that into picture now. So always you start assuming that I have two functions, right? Now I require two functions because there are two variables, right? In the sense the Ez is going to vary with x and y, right? So there are two variables, right? So let the solution, this is the solution. I'm assuming that the Ez is made up of two different, say, variables. It's actually x is a function, y is another function. So that's why I told we need to assume two functions. So Ez is made up of two functions. Again, we are free to choose uh, in any format I want, but the most preferred way is as a product, capital X and capital Y, where I have to make sure that the capital X is pure X. Okay, I'll write in a different way. So let me write it in. It's a pure function of the variable small x. Okay, similarly, Y should be a function of Y only. All right. So it's a pure function of Y. Is it okay? Right. So again, they are independent. The value of x does not depend on y. value of y does not depend on the x. All right, so I'll write x and y are independent. So they have nothing to do with the other variable. Whenever I write about one variable, it has nothing to do with the other variable. Okay, so let me try to write the two parameters I require according to the equation number one. Equation number one says I need dou square ez by dou x square. So let us calculate. So we assume that ez is equal to this. So this implies, let me calculate. So I need dou square ez by dou x square. So this means, right, dou square ez by dou x square means the dou square by dou x square of the capital X and Y, correct? So out of which now you see, since we call they are independent, Y is a constant when you differentiate with respect to X, correct? Right? So Y comes out, right? It is simply the partial differentiation of the capital X with respect to small x. Are you okay? Dou square of capital X with respect to x. So there is a difference. This is my capital X and the denominator contains the small x, small letter x. So that's how I try to differentiate, okay, between the capital and the small x. So right, y times dou square x, capital X by dou x square. So that's the first term. Similarly, we need to write the other term as well. So I also need the dou square Ez by dou y square. It's the same representation, dou square by dou y square of capital X into y. So now x is a constant, correct? So x comes out, it is simply dou square capital Y divided by dou y square. Here also I have capital in the numerator and the small letter in the denominator. Okay, so let's try to write in this. So I'm going to call this 2 with equation number 2. Let's try to put equation 2 in equation 1. Okay, so that means I had a uh, dou square ez by dou x square. So that can be written as y times dou square capital X by dou x square plus the second term was x, right? That's dou square ez by dou y square. I'm going to replace it as x times dou square y divided by dou y square, dou y square plus there is h square ez is capital Xy, right? Equal to 0, right? Now you see what I'm trying to do here is I'm trying to analyze the partial derivative once again, right? My function capital X is a pure function of small x, correct? Right? Could be something like this. Capital X is equal to 4x square plus 3 times x, all right, minus 7. You see, it is a proper function of small x. There is only one variable, right? If, right, I'm trying to do the differentiation of such a function, it is not called as a partial derivative, right? It's actually called as a complete derivative. It's actually normal derivative only, right? I don't have to write a dou by dou x, right? Are you comfortable with that statement, right? That means I don't have to write the dou by dou x is actually in this case only, not always. It is d by dx, correct? It's a proper derivative. Similarly, the dou by dou y is in this case simply d by dy, correct? It's a proper derivative. As our statement says that capital X is a pure function of small x, capital Y is a pure function of small y, there is no meaning for doing a partial derivative. Partial derivative works only when you have multiple variables, right? And you do differentiation with only one part. Others will be considered as a constant, right? Only in that case. But right now, it's not the case. So this implies my equation changes now. So y times d square capital X by dx square plus capital X into this is d square y, sorry, it's a capital Y, mistake. D square times, sorry, d square capital Y by dy square plus h square into capital XY equals to 0. I'll do another modification, that is dividing by capital XY throughout. So when I divide by that, I get 1 by x, right? This is d square capital X by dx square plus this is 1 by y, d square y divided by dy square plus h square equal to 0. Right. Why we did like this? Because now you see whatever I have here is a pure function of x. What we have here is a pure function of y, right? Because right. So and there is a constant value which is a sum, right? So that means this plus this equal to minus h square. Anyway, it can be taken to the other side. So as a sum, you have a constant value. Okay, so what we try to do, okay, again, this is pure mathematics. I'm going back to the basics of a differential equation and the solution of a differential equation. Now you see, it's a proper differential equation, not a partial differential equation. Okay, right. Now, the mathematics says, right, whenever you have such a situation, right, where you are able to separate your uh, variables like this, 1 by x into something, 1 by y into d square y by d y square, right, equal to a constant value of sum. It says that each of the term must be, we have to separate the variables and then we need to solve. Okay, so the maths says that, and we are simply applying what we have studied in engineering maths. Okay, so it says, I'll just write one point here. Uh, okay, let me write a point here for your reference. So this is a, once again, pure function of this is y. All right, so this will be a pure function of this is x, right? So separate the terms and solve. That's the method. Okay, so separate the terms means we'll make another assumption now. So that is 1 by x d square xy dx square is equal to, you can take any value. So I can see that this h goes to the other side. Okay, that is minus of h square. Okay, so I can see that there is a negative term coming into picture. Even if you recall the steps we followed in the engineering mathematics subject, right, there also you assume it to be a negative constant. Okay, it's just because, right, we follow the that's the convention we follow. So what I do, I'll take this as minus b square. Normally we take whatever corresponds to x, you take a minus b square. Whatever is corresponding to y, you take it as minus a square. Okay, so that's the step we follow whenever we solve that equation. In the sense, you see, this is minus b square, this is minus a square plus h square equal to 0. That's my ultimate equation. Okay, so you assume, we have to assume in this way. Okay, right, I'll come back to that. So let this is equal to minus b square 1 by y d square y by d, this is y square. So d square capital Y divided by dy square is equal to minus a square. This implies, now you see what happens to my above said equation. I think I can call that as 3. Let me say this is 4, right? I'm trying to put 4 in 3. Gives, you see, the first term is minus b square. Okay, second term is minus a square plus h square equal to 0. Or in other words, it's the same. I wanted to bring it to this format. That's why we had made a substitution in that fashion. H square is equal to a square plus b square. Okay, this is the ultimate thing I wanted. Okay, so now anyway, you can see that this is a second order differential equation. Okay, this is another second order differential equation. Equation number 4 represents two second order differential equation. First one consists of the it's made up of only x. The second part consists of, right, the terms made up of only y. Okay, so recall, again, this is directly taken from the concepts of differential equations solution, second order differential equations solution. Okay, so how do you do that? So I'll directly write, we know that, right? It's expected to know by this time that what will be the standard format of a solution of second order differential equation. Okay, so we know that the standard solution of the second order differential equation, that is 4, right? In 4 we have two equations, we are trying to write the solution, right? So you see, the capital X will be, right, if you remember this, when I write, you will definitely you'll be able to recall. Okay, so that is a constant c1 into cos the bx. B is present over there because in my equation number 4 you can see that this has right side b square. Okay, so that b is what I'm writing here. Okay, I have some b value, that's what I'm writing, c1 cos bx plus another constant into sine bx. Do you remember this kind of equation? Right, somewhere you might have studied this, you should be able to recall. Okay, it's not, it's in mathematics. Okay, it's an engineering maths solution of differential equation. Okay, similarly I'll write the equation c3, again it's the same thing, it's a cos. Now it is ax because the right side is a. For y equation, right, just consider the equation containing y in equation 4. That's this equation, I'm solving for y, right? The y has the right hand side equal to represented by a square, correct? So the a will come into picture. Okay, so cos ax plus some other constant into sine of ax. So that, this is small letter x. Okay, so this is the standard format, a constant into cos of, right, the right hand side sorry, right hand side of the equation, or the constant present in the equation, right, plus another constant into sine of a term. So you can see that a, yes. Now here we have the following conditions, right, where c1, c2, c3 and c4 are the constant dependent on the boundary conditions, of the waveguide. Okay, right. So now you see, we assumed that, okay, we'll come to the boundary conditions in some time, right? We have to apply because, see, mathematics stops here, right? When we solve the problems in maths, we used to stop at this stage, saying that, okay, I got x, I got y, right? And I also, okay, maybe one more step, not exactly this point. We used to do this. What we used to do in maths, I'll do now. Okay, so this is this final step we used to do. That is, we used to write simply like this. So since we assumed that, right, Ez equal to x into y, I will just write the Ez equation. So Ez is equal to, what is x for me? That is c1 cos bx plus c2 sine bx. This is x for me. You write a y also. Okay, c3 cos ax plus c4 sine sorry, it's my mistake. It's a. Yes, correct. Okay, so this is ax. So we used to stop here. Okay, this is the final answer for us, right? Where c1, c2, c3, c4 are the constants. So we stop there. But now we are actually solving an engineering problem, so we need to go further, and we have to get some uh, method using which we can calculate the C1, C2, C3, C4 practically. So that can be found, right, by using what is called as a boundary condition. So when we apply the boundary conditions, we get the solution. Okay, now let us uh, consider the rectangular waveguide, which we discussed earlier. Okay, we had drawn a diagram, right? I'll quickly go back to that diagram itself. Okay, so this is the one. This is the rectangular waveguide which we are considering. Okay, right? So x-axis, horizontal axis gives the breadth of that. So along that direction, we have a dimension equal to a. So y-axis is a width. Corresponding to that, we have a dimension equal to b. So size along y-axis is b. The size along x-axis is a. And size along z-axis is, as of now, not defined because it can be of any length. Because the wave propagates through that. Okay. Right. Now, so let's try to put some more values to that. Like, so I know that the entire surface of the waveguide acts as a short circuit. Why do I make a statement like that? Because every side is connected, right? So this side, the side on the bottom, right, left side, and the top, they are connected. So that means it is a short. If you connect, if you try to take a path, right, you are able to move around that waveguide and you are able to come back, right? It means everything is shorted. That's why I made a statement, right? The entire surface of the waveguide is a short circuit, right? So in other words, that acts like a ground for our electric field. Is it okay? That's the electric field. It acts like a ground. And since what I am looking at, which wave I am considering now, Ez equal to 0, correct? In this particular case, I am trying to consider Ez equal to 0. Yes, so I am making only one statement now. That makes everything clear, right? Whatever we discussed so far. Okay, so this is the one point I need to remember whenever I try to understand this. Okay, right. Okay, so entire surface of the waveguide acts short or its ground, acts like a short or ground for the electric field, right? That's why I'm writing Ez equal to 0, right? All along the boundary, all along the boundary walls of the waveguide. In the sense, there is no Ez along, right? In any direction you consider, or in any along any surface you consider, there is no electric field along the Z axis. Is it okay? So how many such surfaces you have? I have 4 surfaces. So that means I will get 4 boundary conditions. Okay, what are the 4 boundary conditions? I'll come. Okay, so just to make sure that I'm trying to uh, introduce you to the concept of boundary conditions. Okay, so what is a boundary condition? I'll look at all the boundaries of, right, the waveguide. Okay, at each of the boundary you will feel that there is one condition, one common thing about this whole boundary. You may take the top surface, right? Along the top surface throughout the waveguide there is only one condition. Okay, similarly along the bottom surface there is another condition. Along the right side surface I have third condition, left or left side I have a different condition. So those conditions which you can apply to the waveguide should be satisfied by all the components of electric and magnetic fields in the wave, okay, that are present inside the wave which is propagating through that particular waveguide. Okay, so that's what is a boundary condition. Now I'm writing a boundary condition. Let me write the boundary conditions first, then we will solve. Is it okay? Right, so let's quickly go through. So the first thing, okay, first boundary condition, the number one, first boundary condition is that I'm looking at the bottom plane. Okay, just recall the diagram we considered earlier. It's the bottom plane, in the sense somewhere here I'm going to have a plane, right? This plane I'm talking about. Okay, okay, along this particular plane, I already know that Ez is equal to 0. There is no Ez. So for all the four planes, I'm trying to put the same boundary condition, but I'll slightly modify the uh, according to the coordinate system. Okay, right? There is some fixed value of x over there, fixed value of y over there, etc. Right? You will come to know in some time. All right. Okay. Along this horizontal plane, which is on the xz plane, right? Along this, is it xz plane? Are you able to understand that whatever plane we are considering now is a xz plane, because x-axis and the z-axis, right? X-axis and z-axis, Ez is equal to 0. Okay, x and y will vary, but what is the value of y? Can you tell me along the Ez plane, what is the value of y? So, did you understand my question? Yes, I'll ask a question. You take any point on this Ez plane, okay? Any point you take, what is the value of y? It's 0, right? So that's my condition. You see, along this plane, the condition that I'm going to apply is y is 0. That's all. Y is 0. So in the sense, any component or any part of the wave that actually hits this particular plane will have y equal to 0 is a boundary condition. So when the y becomes equal to 0, my wave touches the bottom plane. Very simple concept. That's all. Okay, so that's a boundary condition. Right, when the wave reaches the boundary, I am able to identify that, okay, if y becomes 0, that means my wave hits the uh, boundary which is present on the bottom plane. That's my first boundary condition. Okay, boundary conditions are very simple actually. Okay, let's try to write that. So first boundary condition is applicable to, I'll write, this is the bottom plane. So what is the bottom plane? I know that I am going to apply the Ez equal to 0 over there, right? Along the complete bottom plane, right? Ez equal to 0. How do you identify that this is a, uh, how do we identify that this is the bottom plane? That is y becomes equal to 0, right? Y is equal to 0, right? Is a one condition, and I have to talk about the x value, right? What can I write? 0 to a, not somewhere. Not, we have a specific value, right? Because x-axis is only between 0 to a. We are very fixed about that. That's all. So you see, I got my first boundary condition. Ez becomes a 0, y is a 0, and x is between 0 to a, means I am at the first boundary. Okay, right, very simple. You understood. Now I'll ask you the second boundary condition. Okay, so second boundary condition, let's try to consider the left wall. Okay, left side that is present on our left side. That is, I'll draw and I'll show you what I'm talking about. So left side is this plane I'm talking about. Okay, this side. Okay, for that, yes, perfect. Then anyway, Ez is equal to 0. Perfect. So let's write that down. So that's how we identify the boundary condition. So this is Ez becomes equal to 0, right? At, you see, x equal to 0 and y varies from 0 to b. Perfect. Now let's go ahead. So I want you to tell me the third boundary condition. So I want to go for a top. Let's go to the one by one. Okay, so from bottom left, then top. Yes. Now you tell me again. I know that in this Ez is obviously 0. Okay. Okay. Y will not vary from 0 to b. Can you check? Yes. Perfect. So y is equal to b and x varies from 0 to a. So give me the fourth boundary condition. That is the, that's all. So once again, I'll write Ez is equal to 0 is my first condition at, yes, can you come back? X equal to a, right? And y varies from 0 to b. So we got, right, all the four different boundary conditions. Now you see, we had another concept in mathematics. I'm trying to relate, okay, whatever we are practically applying. I'm trying to apply this to the math concepts we studied in mathematics, because most of the time in maths we never understood why we are doing that. Okay, now in the mathematics, when we try to solve the equations and we got something like this, right? If at all the question was extended, they used to give what is called as the initial condition. Solve by using the initial condition, something like that. So the same initial conditions now we actually derive. Now, so something like this might be given, right? Ez becomes 0 when x equal to 0 and y is equal to 0. This will be given in mathematics, saying that, okay, solve for this. Okay, but now we are not, we had no idea about what are the conditions we need to apply, but we derived them. Okay, applying to the given problem, we derived this, right? This itself, whatever four conditions we have written here, right? We used to get in the question in mathematics saying that apply these conditions and solve for them. Okay, if you do that, you will get the values of whatever unknowns you have in the equation, c1, c2, c3, c4, right? Those values we used to get in mathematics by applying some conditions given. Those conditions are what we have derived now. Okay, this is the easy. Now we'll do the same thing we used to do in mathematics now to get the values of them. So apply these boundary conditions to our equations. Okay, I'll call this equation by a number so that we can follow that. Okay, that is a 4. So this will be 5. This is equation 5. And the final answer we have is equation 6. Okay, so this is equation number 6. Now I'll give numbers to them. Okay, equation 6, then this is 7, 8, 9, and 10. Okay, so these are the various equation numbers. Now you see, I'm going to apply the boundary conditions one by one to my equation. Okay, the main equation. So the main equation is equation number 6. So right now 7 in 6. Use 7 in 6. That means I'm using the first boundary condition. So first boundary condition says that Ez equal to 0. So my left hand side becomes equal to 0, because equation 6 says that Ez equal to, correct? Ez equal to, right? So left hand side is 0, equal to, you see the first term is C1 cos bx, right? So my x varies from 0 to a. Okay, so I will not put x, but I'll put y equal to 0, right? So that means, see, the c1 cos bx remains as it is, right? Then I have plus c2 sin bx, that remains as it is because it's made up of x, no change in x because x varies from 0 to a, but y is 0, right? When y is 0, what happens? I have the next term, that is, yes, so I only c3, correct? Now you see, this is true for, this has to be valid for all the values of x varying from 0 to a, right? That means this should not be 0, correct? This is not equal to 0, this cannot be equal to 0 because this term should exist for all the values, right? So this implies I can say c3 equal to 0. I understood, right? That means c3 has to be 0. So update your equation. So now whatever I have is the updated equation. This implies the updated equation will be Ez is equal to, right, c1, yes, bx into c4, it is sine, I think ay, correct? Because c3 cos ay plus c4 sin ay. So c3 is gone, right? Ah, perfect, perfect, perfect. Now I'll call this as equation number 11. I'm going to use the next boundary conditions in 11. So I use 7, so I will use 8. Okay, so 8 in 11. Because this is my updated equation, right? Anyway, I got a C3. I don't have to use a C3 anymore, right? Huh. No, 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 I'm trying to find out the values of C1, C2, C3, C4 using the boundary conditions. That's all. It is not for a specific condition. It is applicable for the whole waveguide. Yes. 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 Correct, correct, correct. Yes. So since the wave touches every boundaries, we are using the specific boundary conditions to finalize my equation. Ez. Okay. The Ez remains same irrespective of which boundary it is, right? Ez is the same. My Ez is same because my wave is the same wave I am trying to propagate it through the waveguide. So Ez is same. Okay. So that's okay. Let's proceed further. Now, huh, yes, yes, yes. Now you see the C1, C2, C3, C4 corresponds to the same wave. That's why we are trying to solve it using 4. Okay. So apply the second boundary condition to the updated wave. Okay. That is equation number 11. So I know that in this case, once again, Ez is 0. So left hand side becomes 0. That is equal to. So just look at the second boundary condition and tell me what should I write. So second condition, x is equal to 0, correct? 0 to b. So why I cannot do anything? I have to keep as it is. Yes. C1 cos 0. Yes, perfect. C4 sin ay, right? So y will vary from 0 to b, and this will not be equal to 0 because sin ay means that will not be 0, right? Because as it vary from 0 to b, it's not 0. This implies, right, I can say that this part is not equal to 0. That implies I'll get c1 equal to 0. C1 has to be 0. Okay, well, we'll update further, right? This implies, Ez is it's a product, right? I'll write the constants together. Is it okay? C2 C4 sine bx, correct, sine bx into sine ay. Perfect. Now apply the boundary condition. I'll call this is equation number 12. All right, so let's okay, yeah. So then I'll put 9 equation number 9 in 12. So applying the third boundary condition, I have a left side Ez that is equal to 0 should be equal to what is the condition that you are applying? Top wall, I guess, right? Third condition. Huh. Yes. So y is fixed. So I have to put a y value equal to b. Is it okay? So x varies. So I cannot put any value to x as of now. So let's keep it as it is. So 0 is equal to c2, c4. It's a sine bx. I cannot touch this, but I can definitely write sine ab. Okay. So this means now I should understand something. Now the sine bx is not 0 because x varies. It's not 0 because x varies, right? So when my theta changes, sine theta is not fixed to 0. Sine theta will change. Only at a one point x equal to 0, it will be 0, but other values it's not 0. So this equation says that always this is 0, correct? That means this is not 0, right? So are you getting that point? Yes. Okay. So I'll write this as this is not equal to 0, right? So this is not 0. Anyway, right now I am not able to judge whether this is 0, correct? Because, right, as of now, there are two things. Either this may be 0 or this may be 0, because of which you may have the case. But as of now, I'm not able to decide. So what I do, I'll say that the C2, C4 is also, I'm making sure that it's not 0 as of now. Okay. Let me write that is also not 0. Then that means this has to be 0. Sine AB is equal to 0. Are you right? Let me try to write this. So sine AB is equal to, so let me try to write in this way. Sine AB is equal to 0. This implies, now you see, sine of an angle is equal to 0. Okay. So AB should be equal to 0. It can be pi, it can be 2 pi, it can be 3 pi. In general, it can be n pi. Right? So that means what is, see, my intention is I don't know what was capital A, but the B, I am knowing what is B, because that's the, I think, the height of the waveguide. So definitely that's a known value. So the constant capital A which was not known can be found now, that is equal to n pi by B. Anyway, I got one of the parameter which I can definitely use in my equation to get something at a later stage. Okay, so in this case I am not able to judge whether C, what is the value of C2, what is the value of C4. We have no idea. Let's hold. Okay, let's proceed further. So equation number 12 still remains as it is, no updation for equation 12. Let's put the next condition, 10 in 12. So left hand side is 0. So 0 is equal to, we still have C2, C4. Okay. Yeah. So you told sine B times A into sine AY. Okay. Now I know that sine AY not 0. C to C4 not 0. Correct? So that means the only option I have right now is sine BA is equal to 0. So BA should be 0, pi, 2 pi, up to n pi. Okay. Again, I Yes, I'll make one small change. Let me not take a n here. I'll make it as a different variable m. Okay, it's ultimately one and same. It can be any integer, but n is already used, so I don't want to use it. That's all. Okay, so this means the capital B should be equal to it's some other integer multiple. Okay, m5 by a. All right, so let's go further. Right. So let's try to substitute the values of the equations in the EZ format. This implies the EZ is equal to, right? We have C2, C4 unknowns, right? Sine. It's, I think, yes, it is M pi by A x n pi by, sorry, I'm writing it inside. Okay. So this is n pi y by b. Okay, so you see this is the Ez component value. Okay, it's a it becomes a proper equation only when you give the direction of wave propagation. Okay, now I actually you see I'll try to draw a reference diagram for us. So let's hold on to this. I think what will be the equation number? Uh, Mostly yes, perfect. So this is equation number 30. Okay, so let's consider a wave propagation, right? So we said that this is the z-axis, right? Let's say the wave actually propagates along the z-axis in this fashion. Okay, this is the wave propagation. Now you see, actually what I got, I simply got a Ez component equation for Ez. That's all. Okay. Now you see this Ez, right? It's a component of okay. I cannot write in the Ez. I'll So it's just a component. I'll try to write it in the vector format. Okay, so it's simply a vector, right? So vector's value depends on what x value you have and what y value you have. Okay, it depends on x and y. You can see that depends on some x and some y components in my in the equation number 30, right? In the sense it's a vector. Vectors, so the length of the vector depends upon some constant c2 c4 into sine of, right, that equation, and to into sine of another part. So these two things we understood. Okay, but now you see at every point along this z-axis, right? At every point, here my vector may be like this, here my vector may be like this, here another, right? Right? See, every point you have a different orientation of the vector. Is it okay? So that means there has to be a z term saying that how it is varying, right? Indicating that I need to bring a direction, right? Direction in which the wave propagates, right? There will be right. In other words, I'm saying that I need to bring a z term into picture, right? So in the transmission lines, we have understood that if the wave is propagating along the positive z-axis, you denote that using e to the power minus gamma into z. Correct? Are you able to recall that part? Right? So that means in order to bring the what you call the directionality into picture, right? In this particular Ez component, I have to add the e to the minus z, right? So, okay, we'll multiply e to the minus gamma z. So this is to indicate positive z direction of wave propagation. Right. Now, is it sufficient or do you need anything else? If I simply multiply the above equation by e to the minus gamma z, my equation is complete or not. Okay, the hint to answer this question is that recall the wave propagation chapter in electromagnetic waves, right? There also we had done the same thing. We calculated some, whenever we tried to solve the wave equation, right? We had a general wave equation. So I think this was in the topic where the wave is generated, electromagnetic wave is generated and a source, and it simply entered into the free space. Like, okay, from the sun you have uh, the electromagnetic waves getting radiated, it directly enters into the free space, okay, vacuum. So as soon as it enters vacuum, we solved for the constants like C1, C2 here, right? We solved it, and then we added, uh, first thing we added is the direction of wave propagation. Again, there we assume it was in the x direction, so we mostly wrote it in e to the power minus gamma x. Okay, here we wrote it as e to the minus gamma z. Absolutely fine. What is the next thing we added there? If you are able to recall that, you will be able to answer here. Same thing I'm going to add now, right? Something you need to add. Even if you don't remember that, it's fine, right? You simply think about, okay, wave propagates from sun to earth. Direction, we know the direction. We assume that this is z axis, so we added a e to the minus gamma z. What else the wave takes, right? What else is needed to represent that wave? Just think about that, you will get the answer. Yes, we understood that there's a direction. Assume that this is z axis, so we added a e to the minus gamma z. Hmm. Magnitude is, let's assume that it is represented by C to C4. It's a constant value. Highest value is C to C4. Okay. Yes. What else you need? Phase will ultimately come. I don't have to add as of now. Okay. Phase will come into picture. I'll show you how it is later. Okay. So we'll come to the phase part, but phase is not the answer we are looking for right now. Uh, any other parameter like the on no, not at initial, because we don't think that it is a free space. Okay, right? It's propagating in free space, right? No attenuation. So will you consider how much time, at what time, what is the magnitude? Do you need to consider that, right? Correct. So you need to add a time component as of now, right? Because at what time, where the wave reaches is a parameter, right? That depends on, see, my wave traveling in any direction, right? It depends upon its x axis coordinate, y coordinate, z coordinate, and the time. Because this, now you see, this is not a, yeah. So this is not a 3D case, it's a 4D case. That's why I need to bring the time into picture. So same thing, right? We did there when we solved the second order differential equation, solving the wave equation. Okay, so that's what I'm doing here. So now I'll add the time component. So time cannot be decreasing, time is increasing. So you are always writing e to the power j omega t. Okay, so this is representing the sinusoidal variations of Ez with time. Okay, so that's the last part we are doing here. So that implies equation 12, not 12, I think 13, right? So just now we wrote equation 13. So update the equation number 13 here. Okay. Okay. So equation 13 becomes Ez equals to, you see, C to C4, as of now, we don't have any other solution. That becomes the amplitude of your wave, right? There is no using these boundary conditions, or boundary conditions do not get applied to C to C4. All right. So the C to C4 generates your amplitude. We'll call it as a C. Okay, C sine of this is m pi by a into x into sine n pi by b into y e to the power. You see, we are trying to club the two terms. One is the j omega t, which is positive, okay, and the gamma z, which is negative, e to the power j omega t minus gamma z. Are you okay? Because e to the j omega t into e to the power minus gamma z, will club it. Right? Now you see e to the j theta, right? And this. So this itself is represented as your phase component. You told we might need a phase as well, right? So the solution to the phase comes from this side. Okay. So we have the variation coming up, right? And you see this depends on, right? This actually depends on the dimensions of your waveguide, right? How much variation you have along x-axis is controlled by sine of m pi by a. How much variations you have along the y-axis controlled by n pi by b times y into sine. Okay, so now you got a Ez component. Okay, so there is one more part left, right? That is equation number, okay, let me call this as equation number 14. Right now what I am supposed to do, I have to calculate the Ex, Ey, Hx, Hy. Right. What do I do? What do you substitute? Substitute this Ez in our previous equation. Previously we got, see these equations, right? Ex, Ey, Hx, Hy. Don't consider the H part. We don't have a H at all. Oh, sorry, not in this. The last one should be the previous other one. So Hz, yeah. Hz will not. No, only Ez you substitute. Huh. Yes, perfect. So you will be having this term, this term, this term, and this term. Okay, so we have to substitute if we require the values of ex, ey, hx, hy, right? Inside the in the TM mode. Whenever we say that TM mode is the mode in which the wave is propagating inside the. Correct. So when we move to the other mode, TE mode, we will not be having the EZ, but we'll be having the HZ. HZ will be there, right? EZ will not be there. So we get the values of HZ. We'll substitute. Again, we'll get the EX, EY, HX, HY. Oh. Okay. So if we require, we can definitely do that. But you can take that as a homework for your uh, uh, working, right? Just work that out and get the equation. And I can compare that and give an answer maybe in the next class. Okay, right? So directly you substitute and get an answer and keep it ready with you, right? We'll compare that answer.